For this next calculation, we know that we have added the amount of sodium hydroxide that is exactly equivalent to the amount of weak acid that we started with. And so we're probably going to want to know what that amount is. So remember that we started with 0.00245 moles of the weak acid KHP. And so we're going to need to add that number of moles of sodium hydroxide because the KHP and the sodium hydroxide are in a 1-to-1 ratio. So we need to add that many moles of OH minus to get to the equivalence point. So what volume does that correspond to? Well, we know that concentration is number of moles per unit volume, and so volume of OH minus added at that point will be equal to the number of moles divided by the concentration. The concentration of sodium hydroxide is 0.1 molar, and so if I divide 0.00245 moles by 0.1, I will find that my volume is 0.0245 liters, which is the same as 24.5 milliliters. So the equivalence point occurs at 24.5 milliliters of sodium hydroxide added. Once I know this, I can proceed with my problem by doing the same thing that I did for the other two problems. First, let's imagine what we have in our beaker. So at the equivalence point, we have water, because that's our solvent. We've used up all the weak acid, we've used up all the KHP to make conjugate base. And so we basically just have water and conjugate base left in our beaker. And so the relevant equilibrium reaction that we need to write is conjugate base plus water is in equilibrium to form conjugate acid plus OH minus. And we've already calculated a Kb for that, and so we know that the Kb value for that is equal to 2.6 times 10 to the minus 9. To find the pH at this equivalence point, we'll need to know what our initial concentration of A- is in this beaker when we're at the equivalence point. So after we've added 24.5 milliliters of solution to our 75 milliliters and made 0.0025 moles of this conjugate base. Remember that if we started with 0.0025 moles of the acid and added 0.0025 moles of OH minus, we will have made exactly 0.0025 moles of the A minus because every one of these will react with one of these to form an A minus. And so we already know the number of moles of A minus that we put into our beaker, 0.00245 moles. And at this point, we have 75 plus 24.5 milliliters, or 99.5 milliliters of water. And that's the same as 0.0995 liters of water. And so my concentration of A minus at this point is going to be equal to 0.0246 molar. And at this point, I don't have any HA and I don't have any OH minus because I know I'm at the equivalence point and I know that they've completely reacted to form this 0.0246 molar of the A minus. And so I can solve my equilibrium problem by letting this reaction go to equilibrium by making X of HA and X of OH minus and losing X of A minus. And so at equilibrium, I can see that X represents the amount of products that I'm going to make. My K value is very small, So the amount of products I'm going to make are quite small. So X must be small, and X must be small compared to 0.0246 molar. And so I'm going to ignore the X in relative to 0.0246. And so at equilibrium, I should have the following values. So I can solve for X by plugging into my equilibrium constant expression for the KB and solving for X, which gives me an X which is equal to the OH minus concentration of 7.95 times 10 to the minus 6 molar. And so from that, I can find my POH, and I just take minus the log of that number to find my POH, which is 5.1, and I can take 14 minus 5.1, 14 minus 5.1 to find my pH, and that turns out to be 8.9. And so, at the equivalence point, I have a pH of 8.9. And this is expected because notice that the pH is greater than 7. And that's because we have a base, the conjugate base of KHP, in water, and a base in water produces OH minus, and if we have extra OH minus in solution, our pH is going to be above 7, above neutral.